This is a good hook. I haven't made a space on your worksheet for you to respond to it, but it is certainly worthy of thought. What makes things go? What makes the planets go? What makes the Earth go around? Where's the source of those motions? Worthy of deep thought, and of course, this being a hook, you will have those questions resolved by the end. We start with our discussion of what makes things go by considering this ball rolling in a bowl. This is a problem that Galileo developed. And on your worksheet, if this was a very rigid, low friction bowl, and so too with the ball, if you rolled the bowl from here, it would roll down to the bottom and then roll up the other side. Where would it stop? No friction. Where would it stop rolling and then turn around and come back? But could you draw on your worksheet the spot where it would pause briefly before it rolled back? And then Galileo asked his listeners to consider this bowl, which has this side more gradual than that side. Where here would the ball stop? And then Galileo springs his trap and he says, okay, now do the same for this ball, which is rolling in a bowl which does not have another side. Where would this ball stop rolling? And the point Galileo was trying to make, especially in defense of the Copernican notion of the Earth moving through space, and everybody said, yeah, but what makes the Earth move through space? And the Aristotelian notion that Galileo was battling was that the natural state of things is to be at rest, and if you are moving, then that is an unnatural thing, and there must be something making you move. That if you look out the window and you see a ball go by, you say, somebody must have thrown that ball, because balls don't just go on their own. But Galileo is saying you are wrong. The natural state of things is not to be at rest, but the natural state of things is to continue in whatever motion they have. So you could still go back and say what started the planets moving, but Galileo was saying there is nothing unnatural once a planet is moving, of it continuing to move. That is the most natural thing of all. And that if this ball were to stop, were to change its motion, that would be an acceleration. And that is what would require a force. And so we have what is known as Newton's first law of motion, actually an idea that was developed by Galileo and probably some other people, that an object in motion continues with the same motion, which could be an object not in motion continues with the same not motion, but we have this here. And then this caveat, unless acted upon by a force. That force causes acceleration, and in the absence of force, there would be no acceleration, and so the motion would continue unchanged. More folksy terms, objects keep doing what they're doing. But this is a very profound and non-intuitive idea. Okay. This is also known as the law of inertia. Inertia is something we're going to talk about in just a minute, but that tendency to keep doing what you're doing is what we mean by inertia. Here is Newton's second, and I ask you to state it with the sigma there in front, that actually the way Newton stated it was differently, but the way you will state it will be this, including the sigma. It is the net force that results in the net acceleration of this body, of this object. There is a third law of motion from Newton, but we will study it later. Okay, back to this idea of inertia. And we have a sort of a primitive notion of it, that it is the tendency of things to keep doing what they're doing, or stated in a negative way, the resistance to changing what you are doing is inertia. And I want to take this negative statement here and consider for a moment, what do we mean by resistance? What kind of a thing is resistance? And I hope you recognize that resistance represents a force. Changes in motion. Well, if we mean the rate of change in motion, what is that? And that's, of course, acceleration. So inertia is somehow related to force and acceleration. And I would like to get how they are related. And our tool for discovering relationship is proportionality. We look for that graphing of a functional relationship. Well, proportionality only deals with a pair of objects. And so we're going to have to do that laboratory science thing of holding one of this triple constant and seeing how the remaining two vary with respect to one another. And if we start by holding force constant, then I can look at how inertia is related to acceleration. And when you come back to class, we will do this. I will take a bowling ball and a volleyball, and I will apply the same force to both of them. Which one of these two would you say intuitively has the greater inertia? And I hope your intuition leads you that the bowling ball has greater inertia, greater resistance to changes in motion. You're thinking about trying to get a bowling ball and a volleyball started going, which is what my constant force is going to do. Which one is it easier for it to get going? Easier for the volleyball. Less inertia for the volleyball. So which one of these two, if I smack them both with the same force, is going to have greater acceleration? And I think you would agree it is the volleyball that's going to move more. The one with smaller inertia has greater acceleration. The one with greater inertia has smaller acceleration. That is definitely an indirect relationship. And if we were to actually collect numbers about it, we would find that when you double the inertia, you have the acceleration. That there is an inverse proportionality between inertia and acceleration. Okay, we got a relationship. Now let's keep acceleration constant. I will throw the bowling ball and the volleyball at you with the same speed, and you will stop them both in the same time. So you will produce the same acceleration for both of these. That you will change it from that same initial velocity to 0 in the same time. Constant acceleration. So as you push to stop them, to accelerate them, to slow them down, which one is going to take more force? Is it the one with greater inertia that will take more force, or the one with smaller inertia that will take more force? And I think you can imagine that the bowling ball is going to take a bigger force to produce the same acceleration. That's a direct relationship. When inertia gets bigger, the force gets bigger to produce the same acceleration. If we were to actually gather data, we would find that when you double the inertia, you double the force. So now we have the relationship. Now we can combine them. I hope that you can do that you're not waiting for me to drag it on. That this common inertia is proportional to the force divided by the acceleration. But wait a minute. Force divided by acceleration. You think back to Newton's second law of motion. That is the same thing as mass. So inertia and mass are related. They are not equal. Inertia is proportional to mass. But they are very closely associated with one another. Mass is a bit of a mystery quantity. It's very hard. Physicists are still wrestling with what is this thing mass? Well, one understanding of mass is it has to do with the inertia that something has. There are other understandings of mass, and more recently we have the Higgs boson, which is one more attempt to understand what is this thing mass. It is not a simple idea. I give you mass as the quantity of matter, but that really doesn't say anything. What is it? So, we have this relationship, and ultimately, I would say that the relationship is this, that mass represents the measure of inertia. That inertia is an idea. It is this tendency to keep doing what you're doing. But if you decide to measure it, you decide to put numbers on that idea, and come up with, I have an inertia of 7, that's going to be 7 kilograms. It's the same relationship that we had between this idea that things can move, that things could change their position. Wow, that is so crazy! And then you take that idea of motion and decide to measure it, to put numbers on it, and then you call it speed, or possibly velocity. So the relationship between inertia and mass is the same as the relationship between motion and speed. I hope that's helpful. Okay, moving on to free body diagrams. And long ago, when Mr. Houghton was in high school, he was taught free body diagrams, and he rejected it. He thought it was busy stuff. I don't need this to solve problems. It's just getting in the way of my doing the problem. And when he was in college, when he took physics, he was asked to deal with free body diagrams. And again, he said, oh, come on. And he didn't really embrace them. But as a teacher, I have learned many things. Thank you, oh my students. And one of the things I have learned is that free body diagrams are very cool and very powerful and very important to you understanding what's going on. And I will insist on you coming to a similar feeling about free body diagrams. You can get the right answer without understanding what's going on. And that's not okay with me. It's not okay that you can get the right answer. You need to show that you understand the dynamics of the universe. So here you go. When you do a free body diagram of this event, the first step is for you to identify the body. And maybe it's the person. Hey, he has a body. Maybe it's this box. Maybe it's the boat. You need to decide, and it is a non-trivial exercise. If you pick the wrong body, you will find it will not get you where you want to go, and you will need to go back and restart doing the problem with a better body. Once you have identified the body, And in this case, we're going to use the box as the body. You're going to answer some question like, how hard is the person pushing, or how fast is the box accelerating, or something like that. And from that context, you say, oh, what's going to be useful to me is the box. I want the box to be my body. And then we consider the forces on the box. And of course, for starters, we have the person pushing the box. And I draw that force as a vector which starts on the box and goes away from the box. And I give it a name. Hopefully a name that is meaningful. But if the person pushes the box, then the box is going to push the person. Action-reaction pair. It's got to be. What's another? Well, the boring in all your free body diagrams almost, you're going to have the earth pulling the box down. So there's another force acting on the body. You got to get them all. If you miss some of the forces, you're going to get the problem wrong. But what is this weight, this force? That's the earth pulling the box down. Well, if the earth pulls the box down, then the box is going to pull the earth up. That's another force that's present. But because the earth pulls the box down, then it's going to be the case that the box is going to go smashing into the boat, and it's going to pull, it's going to be a force down against the boat, the box pushing on the deck. But if the box pushes on the deck, then the deck will push on the box, and we call that force the normal force. And finally, perhaps there is friction between the deck and the boat. Maybe there's not. You need to figure that out. You need to be in command of this thing, and you need to get all of the forces acting on the body, not leave any out, but don't put any extras that don't belong. But suppose there was friction. They gave you indications in the statement of the problem to understand that, yeah, there's probably friction here. Then you would have the deck pushing the box back, but of course that means that the box is going to push the deck forward. So there's all of these forces present, and many more. We haven't talked about the other forces on the person and the other forces on the boat, yada, yada, yada. But we only want the forces on our body. You need to be very clear who the body is. And so you do not want to consider any forces which are not acting on the body, even though they are present and acting. And you need to get them all. If you miss one, you're going to get the problem wrong. So you do your best. And maybe as you work the problem, you say, well, this is not working out. And you go back and you say, oh, I left out a force. So goes problem solving. Next, although this is not traditionally a part of a free body, Mr. Houghton feels it is vital, and he will grade your free body incorrect if you do not add this. You need to indicate what acceleration is going on for the body. If the thing is moving at constant velocity or not moving at all, then you need to say that the acceleration is 0. If you think it's accelerating forward, then you indicate that. But it is very important. Now, this vector can't be confused with these force vectors. And so you put it off to the side. Don't put it so close that somebody thinks, oh, you're saying that's another one of the forces. But you put it close enough that you can see it while you're working on these forces. And then finally, having captured all of the forces and the acceleration, then you will work with them. You will work with all of the forces which are going parallel to the presumed acceleration, that all the forces parallel cause that acceleration. And so I would add up the sum of the forces parallel. But if they're going in opposite directions, that has to be a subtraction. And I take the one whose direction agrees with the presumed acceleration, and I will make it be the positive one, and the one that's in the negative direction to that presumed acceleration gets to be the negative one here. And I will take all of the forces which are acting perpendicular to the presumed acceleration, and I will add them up, but the acceleration perpendicular to the acceleration is going to be 0. And so it doesn't matter which one of these you call the negative and which one the positive. Don't make the mistake of thinking that normal force is equal to weight. It is in this instance, but it is not in general. Okay, so I want you to take each of these 4 scenarios, and I want you to make a free body for each of them. Here you have a box hanging on a rope. Free body of the box. Here's a box that's falling. Free fall. What are all the forces acting on that? And in both cases, I would expect you to make a statement about acceleration. Here we have a box being pulled at constant velocity. Ooh, acceleration! What are all the forces acting here? And you might make an effort in all of your free bodies. It's not necessary, but where you think that 2 forces are the same size, you might try to make them, those vectors, be the same length in your free body. It just visually might help you a little bit. And if they're not the same size, you might try to presume who is the bigger one and make it a little bit longer. The difference between these two is instead of constant velocity, now it's being accelerated. So make those free bodies. Oops, and we're not going there.